So now we will talk a little bit about aggregate respiration, about appropriate respiration within aggregates. And Gerhard will talk about the free living. So we do it maybe backwards, but it's fine. We will end up somewhere. So I'm Morten Iversen. I work at the Aggregate Institute in the Marum, and I'm part of the school as well. Can we take a picture? So I think after hearing everybody introducing yourself yesterday, I think most of you know what the biological carbon pump is. I think some of you might already have seen this slide not that long ago. But I will still give a very, very brief introduction. So if you imagine a slice through the water column, you have the photic zone and the aphotic zone. And as you all know, in the photic zone is where we have primary production, so fixed CO2 into organic carbon that can be grazed and respired back to CO2. And this is in the surface ocean, so not the mesopelagic, so we don't really care about it in terms of respiration in sport so much. And I don't care so much about it because it doesn't sink out. So what we're really interested in is when these particles of organic matter start sinking, which can either be phytoplankton aggregates that stick together and form marine snow, or it can be fecal pebbles from zooplankton. These are basically the two main settling aggregates, and they're the one forming the export flux when they sink out of the upper and least layer in the ocean. That we can measure. We just saw Mathieu's presentation where he has sediment swaps. So we can either do it with a drifting sediment swap where we measure it over short time, or we can more anchor sediment swaps on the bottom and then measure over 30 years or over the whole season, and depending on how long we do it, we can get different resolutions and start seeing seasonalities, right? But if we really simplify it, then the amount of flux we get in a certain depth is really determined by degradation or respiration of the sinking aggregates and the sinking speed. This is a very, very simple way of saying it. And this is what we will try to look at today in this talk, or this lecture. First, I wanted to just show a few of the more typical. So we have copepod fecal pellets, which are often these little oval or cylindrical fecal pellets. Then we have krill, which are very long, because krill tend to poop constantly, and at some point it breaks off, and you get these long strings sinking out. And you can see a copepod and a krill here. And then you have the kings of fecal pellets are the salps. They can make these massive fecal pellets, which can sink with up to a kilometer per day, which is a lot in fecal pellets velocities. On the other side, we have the marine snow. It seems a bit more delicious. It's not true, at least, most of it. And this picture shows very nicely why it's called marine snow, right? Because when you shine a light at it in the ocean, it looks like snowflakes. That's what they did with, was it the Elvin? I think where they saw it, one of the submarines, so they saw it the first time. If we zoom in a little bit, you see that they often consist of diatoms that stick together. There is also a little bit of poo in there, often from fecal pellets, which give ballast and make them sink faster. But we can also have marine snow that is formed by animals. So this is an appendicularian. I guess you all know, maybe most of you know an appendicularian. So it has, I don't know if you see it, this is mainly the empty house, but I have a video which shows it better. So you can see the head of the appendicularian and the tail, and then it makes a water current, fill the water up, and it has two filters, a coarse one, which takes out big particles, and a very fine one, which collects all the small particles, and then it eats the small particles. And once the coarse filter is clogged, it cannot use its house, and it jumps out, and it makes a new house. And you can do it up to 20 times a day. And then all these houses start sinking out, and they form marine snow. So it's not just phytoplankton that form the marine snow. As long as you have the organic matter, so this is a picture of bacteria swimming in the free water column. The moment you have some kind of organic matter that can leak out a signal, a chemical cue, often dissolved organic matter, you see how they get attracted to these organic aggregates, and you can see they do this random walk where they swim in all directions, but they try to follow a gradient, and eventually they land on the surface. And this is basically how microbial colonization works. As you will see later, it works best if the particle is more or less suspended and doesn't sink with the activity of the day, because they're not that fast, the bacteria. And once you have bacteria in the aggregates, they start respiring. They're respiring all the time. And just to make sure that we do not think microbial respiration is only bacteria. This is a video from inside an aggregate collected. We get 100-meter steps. You can see it's full of ciliates. Yes, also a ciliate. You see a lot of nanoflagellates here, and you don't even see all the bacteria. And of course, you also have phytoplankton. So you get all these different trophic levels of organisms that all respire, dissolve organic matter, and all of these make up the total respiration of an aggregate. So how do we measure that? So the way we do it, we just saw Mathieu measure in the respire traps. We tend to either collect the aggregates in situ or form them. And then we try to do single aggregate measurements where we use a flow chamber. So we put an aggregate inside a flow chamber, and put a flow from below. And then we balance the upward flow with the sinking velocity of the aggregate so it sits suspended. And then we can measure the sinking velocity as well. We can measure the size in all 3 dimensions, or take a picture of it also. And then we use an electrode oxygen microsensor to measure in very small steps the concentration of oxygen through the aggregate all the way through. And what is important here is that it's suspended, because if you put this on a solid surface, then there's no free diffusion underneath the aggregate. And you can basically get anoxic conditions inside. That's why people believe that aggregates were anoxic for many years, which they're not. They might have anoxic micronesis, but I think I have. And since we don't have the setup here, I put a 40 minutes very interesting detailed introduction about how the flow chamber works. So I suggest that if you want to have a nice glass of wine and watch some movies tonight. And I think that is also, so here you can maybe get a better idea. So we can adjust the flow. This is the flow chamber. And then we have the microsensor here. And then we use a mesh to make sure that there's a laminar flow at the top. And the mesh is just a stocking, a tights, lattice tights, which you can spread out because it doesn't destroy the microsensors and the functions.
What are the balls for?
That's just to prevent diffusion. Keep it some temperature diffusion, keep it warm, but also avoid the evaporation of the water so we don't change salinity too much. But very interesting on the one drive. So then you can get to see here the 2 dimensions, no, 1 dimension. So the distance in millimeter from above the aggregate, the oxygen concentrations, and this is basically the upper part and the lower part of the aggregate. So you can see you can measure in however many micrometer steps you want. So you get an oxygen concentration. At one point, it starts decreasing, becomes quite linear, and this is the boundary layer, the diffusive boundary layer. So it's still in the water, but the water is more or less still due to friction. And this gradient is basically what we're interested in, because we can use this to calculate the flux of oxygen into the aggregate per area per time. And you can also see, okay, I just told you they were not anoxic. So this is a pretty bad example, but often we have 80% of the surrounding oxygen inside the aggregates. So you basically use Fick's law, except we don't assume it should be linear all the time, but you simply uses the change in oxygen concentration over distance times a diffusion coefficient. And then if you go through all the units, you end up with mole oxygen per square centimeter per second. And here you can see an example where it's provided as percentage. So this is a marine snow aggregate, all the courses will be an oxygen measurement. And you can see we still have 82% of the surrounding oxygen at the center of the aggregate. So what you have to do once you have your flux, mole oxygen per area per time, is just to know basically what is the surface area of an aggregate, and then you multiply the two, and you know what the total respiration is. So oxygen flux times surface area is total oxygen consumption. And then it's super easy. Now you just need the correct respiratory quotient to convert into CO2. That's somewhere between 0.8 and 1.2, so I tend to put it at 1. But that's the first uncertainty that we have in all of this. If you do that, here it says respiration rate in microgram carbon per day per aggregate. And then we take the same aggregate we measured. After that, we could also look at it under the microscope. But we take it and measure the carbon content using elemental analyzer or something similar. Now we know this aggregate, we measure the respiration, we have a carbon. So we can do this for all the aggregates, and we tend to actually get a quite good correlation between the two, if it's at the same temperature. And if we divide them, bacterial carbon respiration against the particulate organic carbon content, we get what we can call carbon-specific respiration, or I often just call it degradation rate. And when we plot that, so this is in per day, because here you get microgram carbon per day per aggregate, divided with microgram carbon per aggregate, so it's the loss of carbon of the total POC that is converted into CO2 per day. And here, it doesn't seem to be size dependent at all. It doesn't even, and I know that we might have to discuss about it also with material, because I think you see something else in the respired slabs. But we really see that it's temperature dependent for sure, but we don't see a big change between aggregate size or aggregate sizes. And it's quite interesting why there are these differences. And the next step you can do once you have your carbon specific. So now you know how much is respired per day, right? But if you want to look into flux, so flux attenuation, you need to know how long does it stay in a certain depth of the ocean. So for that, we use the sinking velocity, the sinking speed meters per day against the diameter of the aggregates. In this case, there was a quite good size relationship. It's not always the case. And if you now divide the carbon-specific degradation rate with the sinking speed, you can get what the fraction of carbon is, particularly organic carbon, that's respired into CO2 per meter that it settles, which we tend to call L ratio, or it could also be called a degradation length scale. And since we have a strong size dependency in the settling velocity, we see that the small particles will be degraded more per meter that they settle compared to the large particles. So just in terms of microbial degradation, we would assume large particles to sink out in this case. Then there are other factors which we don't go into here. But if we simplify it, we saw no size-dependent carbon-specific degradation. It seems that increasing sinking speed would increase POC export. And we can make a little example where we can take a 1 millimeter aggregate with sinks with 90 meters per day and compare it to a 6 millimeter large aggregate with sinks with 570 meters per day. We see that there's an order of magnitude between the degradation per meter settled, and when half of the POC is respired, the small one will be at around 500 meters and the large one at 3,000. So that's easy. So why is it so difficult to model? But then the problem is we compare it to actual measurements, and then we have our perfect degradation here, but that's not what is happening at all. So something else than just microbial degradation is taking care of the flux attenuation. That could be zooplankton, it could be critical retention, disaggregation, we don't know actually what it is. But we can try to guess at it. So this is a data set from Northwest Africa, where we use camera profiles. It's all the open circles and sediment traps with the water column to try to get a high resolution of fluxes. And just like in the Turk set, we tried, again with several assumptions, but we tried to kind of estimate the different degradation rates through the water column. And because we had camera profiles, we could do it for day and night separately during the study, so we could start seeing differences. And if we start with basically the upper mesopelagic-ish, we find that we had around 12% carbon-specific degradation per day. So we tried, now I have to see because it changed. Okay, still. And we think this is basically the same. So we see during day, they're pretty much similar in the upper 130 meters and down to 220. At night, it's much higher, but we don't really expect bacteria to change their activity between day and night. So we assume there's still a part of this that says the microbiome. So we try to compare with the same temperature to laboratory measurements. And here we have marine snow in situ collected, laboratory forms. I think we have some fecal pellets, all kind of aggregates we have measured with the microsensor. And we basically find 13% in the lab and between 12 and 13. So we assume that this part is probably microbial degradation at around 15 degrees with low pressure. If we look at what is happening at night, then this region has very strong zooplankton migration. So we assume that the zooplankton, and just to show a little copepod feeding on an aggregate, and you can see they're very excited about finding particles. So I think they could maybe make up the 46%. But this is not about zooplankton, unfortunately. So we go a bit further down. So what you see in the deep ocean, and this is also what Mathieu said with the temperature dependence. So we got quite a lot lower, actually. And that's why we actually did this study from 2013, where we were looking at the same aggregates. So we made the aggregates in the laboratory, kept them in a water tank. After a certain time, we shifted half of them to 4 degrees and kept on measuring them over 3 weeks, I think. And we basically saw the shift down to this 2 to 3% degradation, which fitted with the in situ. And so we assumed that we basically had 3.5-fold reduction in microbial degradation with 10 degrees temperature decrease. This sounds a lot like Q10, but since I only had 2 time points, I couldn't call it Q10, so that's why I phrased it like that. But we have seen that since, so there's around 3.5 in Q10 for settling aggregates. Back then, it was always assumed that when a particle sank, bacteria would jump on and off and only remain there for 20 minutes. So that basically means you should get deep sea bacteria onto the aggregates, and they should be adapted to the deep ocean. We were a bit surprised about this big change, but we knew that our laboratory study did not have deep sea bacteria. So we basically took surface bacteria and exposed them to cold temperatures. But we didn't know why we saw the same in situ. So we decided to collect aggregates at different depths. And this was, you can't really see the reference, but we published it in 2015, where we collected aggregates using gel traps. And then we used fluorescence in situ hybridization to really count and see the different bacteria and compare it with the free living. And what we found was the aggregates at 100 meters were very similar to the fluorescence maximum bacterial community, whereas the ones at 400 meters were very similar to 700 meters, which was 10 meters above the seafloor, so basically the surface sediment. But they were all different to the free living in the mesopelagic. So we concluded that attached microbial communities are inherited from the fluorescent maximum, But there are some changes, and these changes are due to internal competition or growth or micro niches that favor somebody more than colonization at depth. And these are some of so we were slicing individual aggregates and staining them with fluorescence in situ hybridization, and then using a confocal laser scanning microscope. And all the green dots are the different types of bacteria, and the yellow is the autofluorescence. So we could start seeing what the 3D distribution was. And then since we did it using molecular techniques, and other people have done it, and everybody seems to find the same. And now it's termed vertical microbial connectivity, where we really see that often you have this surface signal from the free living, which continues all the way down to the basal-pelagic inside the bacteria, but you have a huge unknown group, which are these microniches or maybe special environments that support some microbes. So it really seems like attached microbes within aggregates in the deep are inherited from the surface, and there's only little colonization in the deep ocean. So this could explain why we have low respiration, because they're really adapted to the surface. And then, of course, you have pressure effects, which is coming on top, which I think Gerhard will talk about. But we were a bit interested in why do they not colonize? So we started collecting aggregates and started trying to look at the diffusive boundary layer or the velocity boundary layer around an aggregate using particle emitting velocimetry. I have a video showing it better here. So this is a single aggregate. And here you have neutrally buoyant particles, which you can see are kind of coming around. And you really see that there's actually no water flowing through an aggregate. It's all being pushed around. So you get this boundary layer around. And in order for a bacteria to colonize an aggregate, it basically needs to be able to swim. So it needs to be able to cross this boundary layer and then attach it in the deep ocean. So only motile microbes can cross the boundary layer around settling aggregates. But then we were still, even though there's only a few microbes that can do that, technically there should be quite a lot more attaching than what we see. So we thought maybe we need to really try to scan. So we scanned an in situ aggregate using NMR. And here you can see only the surface. And here you see the whole pore space only. So there's a lot of pore space inside these aggregates. And then we used it to really model the flow to figure out how is the time that water can remain next to an aggregate. And when we model it, you can see the residence time, so the duration that water stays at a certain place. And it turns out it's much longer behind than at the sides and at the front. So it really seems for bacteria to be able to colonize, it needs to colonize from the back of a sinking aggregate. And the same with scavenging, maybe clay particles or something. It's a little bit counterintuitive. But that also means that you reduce the area that they can actually attach, right? So we found, so actually, the bacteria need to be able to swim to attach, and it's only a few percentage of the deep sea bacteria that actually can swim. And then we found that the retention time of the boundary layer is longest behind. And when we really calculated out, for an aggregate to sink through 1,000 meters of water column, depending on the aggregate size and settling velocity, but it's only a few percentages of the total abundance that could actually exchange with between the free water and the aggregate in the deep ocean. So it kind of makes sense because it's only 5% of the total abundance that could be new or colonized. We wouldn't really see it statistically anyway. So we're not excluding that it happens, but it doesn't seem to be significant. So these are all a bit of lab measurements, and what we have been working on, this is the last 2 slides at the time. So we are trying to take all these types of measurements and do it automatically, a bit like Mathieu is also doing and Dominique, and try to have an instrument we just put in the ocean and it does it automatically. So we developed this bio-optical platform, we call it. So it has a settling column. You just saw an aggregate sinking through. Maybe I started again. So basically here it's a little bit like a sediment trap. We have a settling column, a camera, and then we can measure sinking velocities and sizes of different aggregate types. Then we have 41 little cups filled with a viscous gel, so we can preserve the individual aggregate. And we deploy it for a year at a time. So that means we can get 3 days to a week, depending on how we time it. Collection of the different aggregates. So twice a day it switches on. At the moment it's in the Arctic. And it measures the sinking velocity and size and collects these aggregates and preserves them individually. So we actually have each single aggregate after a whole year, which we can take out and do sequencing and look under the microscope. And here are some examples of what we caught. And we have deployed it at Northwest Africa at the Porcupine Abyssal Plain Observatory of West Ireland, and here in the Fram Strait in the Arctic. And here are some of the sinking velocities we have been getting, and some examples of the aggregates. So it's kind of interesting to see how different the size and sinking velocities are. We haven't quite figured out once we're controlling it yet, and that's what we're looking into now. And the next step, this links to the respiration, is that we are now going to use optodes. So we have developed a system where you basically have a gas-tight cup. So we allow the aggregates to sink in, also maybe over some days, depending how productive it is. They land on a little mesh below, and then they start using the oxygen. And we are hoping, based on the gradient and the oxygen concentration in the free water, we can calculate what the respiration is. We've done some laboratory tests that we can see that it takes a little longer than we thought for steady state. So there's something we need to look into. And at the moment, we're trying to model it and see if maybe we need to make the chamber much smaller than it is or something. So we are hoping to be able to then have size and settling, types of aggregates, and microbial respiration and carbon content of, and have that also matching anywhere. And that's it. This is summary. So, in a summary, microbial respiration of aggregates is not just bacteria, but it's all aggregates, all organisms within aggregates. The carbon-specific degradation of settling aggregates, at least in our case, doesn't seem to change with aggregate type or size. Carbon-specific degradation decreases with decreasing temperature, which is maybe not a surprise. But there's a lot of unknown. This is why we're training you, so we hope you can answer this. So pressure, I think Gerhard will tell you that he has some numbers already. But what about the composition of organic matter, quality, the stoichiometry, micrometers? I said they were not anoxic, but there are anoxic micrometers inside where nitrogen cycling seems to take place. What about the trophic interaction over time? So all these microbial communities, how does that impact? If all the bacteria are grazed, there's maybe less recycling, mineralization, but more respiration, etc. We don't even know how much dissolved organic matter is released from these aggregates. And then, of course, the respiratory quotient, the conversion from oxygen to carbon dioxide is always a weak point. That's it.
How long does it take to